All right, so I want to welcome Petar Veličković to this special edition of Zeta Alpha Trends in AI. Petar is joining us from London, where he is a staff research scientist at DeepMind. And so, first of all, welcome to this special edition of Trends in AI. Can you tell me a little bit about your background, kind of how, I'm especially interested how you got into interested in AI and eventually through your journey on geometric deep learning and all got interested in algorithmic reasoning, which is going to be the topic of our interview today.
Thanks so much for having me, first of all, Jakub, and a great hello to both you and everybody listening to us. I would say that essentially it's a bit of an interesting story because it goes in on itself. I kind of started out as a theoretical computer science student at Cambridge for my undergraduate, and the way in which I started to do computer science, the way in which I would argue many people who come from our regions in Central and Eastern Europe get into computer science is through algorithms and through competitive programming and data structures and these kinds of things. So basically, for those who are unaware, it's basically these kinds of competitions where you're supposed to write a program that solves some particular task, given only language input and maybe a few examples, in a way that it terminates with the correct answer in a certain amount of time and in a certain amount of memory limits. So it's kind of, you have to quickly learn how to write efficient programs. And for a very long time, this is what computer science was to me. So when I started my studies in computer science, I specialized mainly on algorithms and data structures and the related theoretical fields. And I assumed that I would probably have a career in software engineering when I initially started. I first got exposure to AI when I started doing my final year project at Cambridge for my bachelor's. This was with Pietro Leo, who ended up being my PhD advisor as well. I wanted to do a project in bioinformatics because I knew that bioinformatics and biology generally was full of classical algorithms. So I thought it would be a great way to kind of apply what I have learned and what I know well. But my advisor very quickly convinced me that in reality nowadays, and very quickly, it's getting to a point where the dominating method in computational biology is not classical algorithmic, it's actually machine learning. And this is what got me to first seriously consider studying machine learning and artificial intelligence. I really enjoyed doing it because I saw it as a kind of natural next step to, me being able to program a machine to do something. Now it's me being able to program a machine to learn by itself how to do something, which I thought was quite fascinating and obviously had a lot of interesting applications. So shortly after I got my bachelor, I continued at Cambridge as a PhD student in machine learning together with Pietro. And this is how my interests in AI were originally created. The expansion into geometric deep learning, well, through graph neural networks, happened only a few years later. First, during my internships at Mila in Montreal, when I worked with Joshua Bengio, Adriana Romero, and Devin Helm, where we got to touch upon these ideas of building machine learning models over data that is irregularly structured. So unlike the more popular kinds of data like text or images or speech, we were now building models that worked over arbitrary graph structures, which I found to be extremely powerful and generally aligning quite well with the kinds of graph algorithmic things I used to do when I started doing computer science. So I really enjoyed it. And it kind of felt to me like this was a very general way to reason about machine learning computation. So I thought it would be a good investment for the years to come. And then only many years later, when I got in touch with Michael Bronstein, John Brunner, and Taku Cohen, I started to connect the dots about how these graph neural networks are just really an instance of a more general geometric deep learning blueprint that allows you to build neural network architectures over arbitrary input data with arbitrary symmetries. GNNs just happen to be the version of geometric deep learning for graph structured inputs and permutation symmetry.
And, congratulations, by the way, on the very nice book that you guys have produced in that area.
Thank you. I mean, we have yet to make it into a book. We did get the all clear from MIT Press, and it will be published as a book with MIT Press, but we still need to actually write the full book version. But yes, for the time being, we have the proto book, which is about 50% of what the full book is going to be. So thanks for that. And yeah, how did algorithmic reasoning come in the whole picture? Again, I then realized that the same way we talk about symmetries in machine learning. So if I use some symmetry transformation on my input and apply a neural network, then ideally it should be the same output as if I first applied the neural network and then applied an appropriate symmetry transformation. This is known as the equivariance constraint. I already saw how this can be seen as a somewhat special case of the preconditions and postconditions of algorithms. So if I give you an algorithmic input that satisfies certain kinds of conditions, when I talk about algorithms, I can often think about one step of the algorithm satisfying some different kind of condition when it terminates. So it was a natural way for me to, through the lens of GNNs and geometric deep learning, start studying, can we teach machine learning models to execute exactly those kinds of algorithms that I really enjoyed playing with when I started my career as a computer scientist. So yeah, in a way, I've gone full circle, but it's not just, it started out as a toy problem kind of investigation, but I think we're actually only starting to scratch the surface over something that's potentially really powerful with these kinds of models. So yeah, I'm really, really excited about what's going to happen in the coming few years or months even.
Back to the roots in some sense, but now for serious with the full machinery that you learned about and invented to some extent. I was really curious, like you kind of coined the term neural algorithmic reasoning, right? And I've been in AI and cognitive science for some 30 years now, and I'm always a little bit weary of the term reasoning. Like, what is it exactly? Are we talking, like logic and algebra here, or like common sense reasoning, human reasoning? Can you explain a little bit like how you see the connection between algorithms and reasoning?
That's a very good question. And it's really something that depends on the perspective of the person you're speaking to, right? For me, who was basically trained to work with data structures and algorithms for my undergraduate training, I actually see algorithms as a very neat way to formalize various kinds of decision making and strategies and these kinds of things. So maybe with algorithms, we won't be able to express all kinds of reasoning that one might think about, because it's not necessarily always going to be rational or deterministic or something like this. Like it's not always clear cut. But I think that algorithms are a very useful description language to talk about all sorts of reasoning procedures. And maybe more importantly, they're a language that's going to stay relevant no matter what the model of computation is, right? Are you doing it on a CPU, on a GPU, on a quantum computation, TPUs, whatever? Like the models might be different, but the language, the abstract language, is very likely going to stay the same. And because of this, I thought that algorithms are a very nice way to think about complex sequences of decisions that need to be made. And
you see it kind of as a way to describe, let's say, reasoning on mathematical objects and their structure in some.
At the lowest possible level, yes. So the way they're defined in the computer science literature, they operate over abstractified mathematical objects. But in my opinion, one of the potentially coolest promises of neural algorithmic reasoning is to then, like, being guided by that kind of realm where everything is nicely defined and delimited, to then break away from the realm of these abstractified, well-defined mathematical inputs and build the models that might be applied in the real world. So over noisy, raw, complex temporal data, right? This is the real dream. But when we think about the core part of what algorithmic reasoning is all about, it is talking about reasoning over these well-defined mathematical structures. Yeah.
And there's a lot of criticisms of modern sort of deep learning based AI paradigms, exactly on the grounds of reasoning and kind of the symbolic aspects of reasoning and logic being absent, or also sometimes directed at the sort of lack of common sense reasoning, right? So do you see your work on reasoning kind of contributing towards addressing those criticisms?
Yeah. So that would definitely be a dream, let's say. Like, I would like to, using some of the directions that we're building, maybe even one day be able to give like robust guarantees about this network will terminate in a certain amount of steps. It will be guaranteed to give us answers within this level of tolerance and these kinds of things. We are currently unable to do that. So the systems are still from start to finish, end-to-end trained neural networks with the gradient descent. So all that we do will inherit the same kinds of limitations that these models currently have. That being said, the method that we propose is a bit of a, let's say, best possible way that we've been able to think about so far to capture the computation of some actually rigorous algorithm for which you have, clear generalization properties and, proper step-by-step thinking and things like that, to take the essence of what those algorithms are and to then put them in a setting where you can easily sort of train things using gradient descent. So let's say, yes, the hope is definitely to provide an answer to these kinds of directions. I'll just say with our current blueprint, we're maybe not able to decisively answer those kinds of questions. But in the future, I would very much like to be able to.
Yeah. So the reason we got in touch for this interview is actually this paper that you recently published with your colleagues from DeepMind. The CLRS Algorithmic Reasoning Benchmark. It was published on Archive in June and presented at ICML, right, in a month later. And it really creates a resource for a whole program of both empirical, computational, and theoretical research. So a very nice paper. By the way, CLRS, for those in the audience who are wondering what it stands for the last names of the authors of the classical Introduction to Algorithms book, Carmen, Leserson, Rivest, and Steen. So Petar, maybe you can explain to a broader audience kind of the core idea of the paper and what you hope to achieve with it.
To truly answer what brought us to this paper, I actually need to take you back like 2.5 years in time, right? So this was, around the time when the pandemic was, starting to get real. We all started to work from home. I basically, at this time was starting to work on algorithmic problems, and we were able to publish basically 2 papers around this time, which dealt with various kinds of graph neural network variations that were able to fit certain classes of algorithms better. However, this turned out to be quite nice. Like, we got to publish these papers at top conferences. There were some other groups also very actively working on this. I think Steffi Egelka's group at MIT is an excellent group of people that have quite intensely worked on this, not just empirically, but also theoretically. They developed some really cool theory around this that shows why it's a good idea to use GNNs to fit algorithms in the first place, like, let alone the empirical results. But one thing that always struck me as a bit of a problem, because we want to make it known for everyone that training neural networks and algorithmic problems is worthwhile, even from the perspective of if you just want to benchmark your model to see, like, to what extent can it solve these kinds of standard things that we know are, in the standard software engineers, toolbox, right? But also from the perspective of, can we then, as we said, take these models and plug them into meaningful real-world problems, right? And I saw one thing as a very big impediment to that already, in the year 2020, which was that you have all these cool papers floating around, but every single one of those papers proposes a new variation on a GNN to solve a certain class of algorithmic problems better. And to show that it works, they build their own high-quality targeted data set for this particular category of reasoners. And then they train a model on that and they get a better performance or something like this. And that's the paper, right? So every single paper proposes its own data set. And this is a bit of a problem for 2 reasons. The first problem is that it's going to be really, really hard to track progress in the area if you do things like that, because everybody will choose the baselines that make the most sense for this particular class of problems, but there's no regression test, so to speak, right, about if I improve performance on one class of problems, am I catastrophically injuring performance on other classes of problems, right? This is a very important thing that papers just simply weren't considering to that extent before. And secondly, these are very high quality papers from great groups, and the data sets, themselves are, I've read these papers, the data sets were very good quality in terms of how they were generated. But the problem is, if you're someone who comes into this field, and, as I said, we want all of machine learning, all of the practitioners in machine learning to be aware of these kind of opportunities and to try to battle test their models on them. Let's say you're someone who hasn't had a formal training in theoretical computer science and you want to enter this field. How do you do it? how do you even generate a data set of meaningful problems if you're unaware of what kinds of meaningful algorithms are there that probe a particular kind of reasoning, right? I previously had a paper at NeurIPS titled Pointer Graph Networks that basically looked at pointer-based data structures. I knew immediately, like when I started thinking of this paper, what was going to be the task where I test this on. I knew it was going to be Kruskal's algorithm for spanning trees. That's the most obvious case of a pointer-based data structure that improves performance in an algorithm. If I did not have a degree in theoretical computer science, would I know how to do this? Probably not, at least not as easily, right? So what we really wanted to do also is not only to unify evaluation across different papers, but also to democratize access to this area, to make it easy.
How do these data sets actually kind of look in practice? So how do you encode this kind of algorithmic challenge to a learning problem?
Yeah, so basically, because you're fitting an algorithm, you know you have a target function. It's basically the code that implements the algorithm itself. And then the idea is you generate inputs from certain chosen distributions of inputs that you care about. And then you run the algorithm on those inputs. And that algorithm produces the output that you can take as a label. But very importantly, the algorithm also has some intermediate states. And if you truly want to fit the algorithm's direction, you are also going to be interested in that entire trajectory. Why is this important? Think of sorting algorithms as a classical example. Every single sorting algorithm implements exactly the same function. So if you go from input to output, it won't tell them apart. But insertion sort, heap sort, quick sort, merge sort, they all have different logics that let them arrive at this answer. So providing the intermediate trajectory is very important. And that's actually another area where even if you have the algorithmic knowledge, if you're able to find what algorithms are most relevant, you might not necessarily have the easiest way, and it's a bit tedious to decide where in the middle of the algorithm do I choose to capture data and which data do I capture. These are all very complicated decisions that might make it complicated for someone entering the field without proper training to interface with the area in the most meaningful and reliable way. We wanted to make it possible, like out of the box, to take an algorithm, to take a model, and to immediately get results without modifying anything, right? So that's really partly what CLRS is all about. Like, we built a data set with 30 algorithms with 5 or 6 different baseline models. And the algorithms automatically support capturing data at the most interesting intermediate points. So you get full access to trajectories like that. And each, like the way the benchmark is designed is for every algorithm, you have a very clear specification of what are the inputs, outputs, and intermediate states. And they all have to conform to a given type system that we have. And what does that type system give you? It tells you exactly what are the encoders, decoders, and loss functions that you're going to need for every single one of those objects, right? So basically, giving the algorithmic specification and the code that actually executes the algorithm, and the sampler that decides the input distribution, our library does everything else. It automatically builds a neural network model that can run over that algorithm and the loss functions and all those things. You don't have to think about that. You just need to provide a spec of the algorithm. So yeah, this was our aim, right? To provide.
In the paper, you mentioned also the way like you can give hints to the algorithms in the data set. Can you go into that a little bit more?
Yeah, I mean, we've basically already covered it, because hints are how we internally refer to these intermediate states. So like, you have the whole trajectory of the algorithm, and we call them hints because ultimately you want to go from the inputs to the outputs, but these intermediate states are kind of intermediate hint signal that pushes your representations towards what the algorithm would be doing internally. So that's why we call them hints, as a kind of shorthand word for intermediate trajectories, but really they're the same thing.
Right.
Yeah.
And so you define this benchmark, right, which makes it possible to kind of improve over time and do this sort of competitive programming contest for machine learning researchers in an indirect way. So obviously that gives you some scores, right? Like, so what does it mean for one of the learning algorithms to achieve a score of 50 or 70 on an algorithmic reasoning benchmark around a single algorithm?
Yeah, so that's a very good question. And there are actually many ways to define it. We offered one particular way in our set of experiments in the code we publicly released. But the code is so extensible that if you want to write a different evaluation function, that will be quite easy to do. So specifically how we compute things is like you have, as we mentioned already, the algorithm has certain outputs that you need to predict for various nodes, edges, or whole graph inputs of your data. And what we currently do is for every single point where an output is defined, we check whether you got the correct output or not, and we compute the micro F1 score of all of those predictions. So to kind of account class imbalance, because that happens quite often also. Yeah.
So does it mean like when you that you can kind of learn an approximation of the algorithm, but it's not really the algorithm in that sense?
Yes, that is true. So to go back to your question, if you say I have 70% accuracy, 70% F1 score on a sorting algorithm in CLRS, what it currently means is that over all of the list entries in your test set, you are predicting the correct predecessor in a sorted list 70% of the time. Yeah?
Right.
So that's what it means, to be very precise. Now, some people might prefer a different metric. They might say either you've sorted the array or you didn't. This would obviously give you a lower F1 score, because now you either have a 0 or 1 for the whole array, whereas in our current evaluation, we say one element is correctly sorted if its predecessor is correct. Yeah.
Right.
But that's
and I noticed that in your evaluation, you had very high scores on the validation set and quite significantly lower on the test set. What does that mean?
So this is, by the way, the reason why I found it necessary to even create a new name for all of this, right? Because all we're doing is supervised learning, behavior cloning, all of these things already exist, right? That's as terms. So why do I need to create a term neural algorithmic reasoning? Well, I think the main reason why is because when you want to fit an algorithm, which is a target function, the game is changed. It's not like usual supervised learning where you might have a test data set you care about and you want to just maximize your performance on that test data set, which is often somehow related to the distribution of your training data points, right? With algorithms, to say that you fit an algorithm means that you fit that algorithm everywhere, right? Like algorithms don't collapse if you give them inputs that are 4 times as big, for example, with our current test set, right? So if you really want to check to what extent is your neural network reasoning, you need to check how does it work over bigger inputs? How does it work over inputs that are distributed differently? I believe this is a failure mode for many currently popular models that claim to do reasoning, right? So, and our benchmark just clearly shows it in this very nice noiseless regime with perfect stepwise supervision given to you. So you don't have to worry about any perception. It's just pure reasoning. Already there, we go from basically almost 100% validation to 50%.
Right. So the distribution of the example is fundamentally different in the test and validation set.
Exactly.
Right. And one other aspect I was really interested in, which you may speak about a little bit, is like, okay, so these are very different algorithms, right? And even like different learning algorithms do have different scores on all of them. To what extent do you see really kind of cross-task generalization, like transfer learning from one algorithm to the other, which I think in the introduction to the paper you kind of allude to that being the holy grail of the whole thing, right? Like being able to compose algorithms out of subroutines, elements, reusable components.
That's a great question, and I agree with you that that's where we want to be. The CLRS paper in and of itself doesn't test in this regime because like we could already barely squeeze the experiments onto 8 pages as it is. Like it would have been very hard to also pick and choose which transfer experiments to do. So for CLRS itself, I don't have an answer to that question, but generally speaking, people have been playing with combinations of algorithms in several previous papers, and I have previously co-authored a paper at NeurIPS last year, which was titled How to Transfer Algorithmic Reasoning Knowledge to Learn New Algorithms. And there we basically showed that under certain types of multitask training, you actually can get very meaningful positive transfer from certain classes of algorithms to other types of related algorithms, right? So this is definitely possible. We don't currently have a clear published evaluation of this over CLRS, but I am certain that something like this will happen in the very near future.
So is that kind of the challenge to the field to go in that direction to improve the submissions on the benchmark? By the way, it's a benchmark, but I didn't see like a public leaderboard. Did you get any submissions from somebody else? Do you plan to have a leaderboard?
Yeah. So, okay. So 2 points to be made here. The first one is that this is definitely a challenge for the community to try to show interesting transfers between types of algorithms. But I'm also a firm believer in, to some extent, you should learn to walk before you can run. And our paper already shows, even for single task where everything is known and given up front, we drop half the performance when we extrapolate, right? So that's the first challenge I would give to the community. And then once we get better at understanding why does this performance drop so much, then we can talk about combinations and transfers, right? So this is my thinking, right? And in terms of the benchmark, so we call it a benchmark, but it's actually a benchmark factory, right? Because for a specific algorithmic target, a specific data sampler, and a specific type specification, you can generate your own benchmarks within CLRS, which I think is the really cool thing, right? So it's not a static data set. We do provide one static data set that we use to generate data for our particular paper, but we are deliberately not making this a server where people can send submissions, because that's fundamentally not what we want. Like, we don't necessarily want, if someone wants to evaluate a general purpose reasoner on a reasonable set of data points, they can reuse the data we used. We actually provide it as a zip file that you can download directly, right? So you don't have to generate anything. It's actually even faster if you do it that way. But we don't want that CLRS 30 benchmark to be the be-all, end-all, right? We want CLRS to be used by people to create combinations of these algorithms, distributions, and tasks that are best suited for what they want to do, while also making sure they stay honest by letting them evaluate over things that are not what their paper targets, right? So I really see it as a generator of benchmarks rather than a benchmark in and of itself. That being said, we are in discussions with the OGB community, the Open Graph Benchmark people from Stanford, where maybe we might find a way to create an actual proper leaderboardable benchmark out of this specific thing we put in this paper. But basically, we thought that making it, a more formal benchmark would send the wrong signal into the community. We did not want people to think this is what we need to beat right now, but more like, here is a great thing you can play with, and if you want, there's this one specific thing that came out of it, right?
So going back to your early days, it's not a competitive programming contest, it's a fundamental research program.
I'm staying honest to my current position as a research scientist, right? So I fundamentally want people to look at this as a research challenge, yes.
Right. Well, thanks for the great paper, and thanks for clarifying it. Maybe as a kind of ping up, this is a great resource. It's a very interesting research direction. If you speculate a little bit and look into the future, so if you look at kind of human thinking, right? At DeepMind, you guys are executing a very long-term research program aiming at sort of general intelligence. And one of the aspects that humans are not particularly good at is reasoning. In fact, for algorithmic reasoning, you need many years of schooling, right? So can you reflect a little bit on the way sort of deep learning architectures and algorithmic reasoning are inherently compatible or incompatible, and how kind of, how simulating these kind of formal machines on deep learning style architectures will bring in the future in your vision?
That's a very good question. We outlined some possible visions in the neural algorithmic reasoning position paper, which I think we also cite within CLRS. So it's a fun read. There's no maths in it, just thoughts and visions, I guess. But the general idea is that with these kinds of directions, you can learn a sort of library of behaviors, right? So the whole CLRS textbook, which is, thousands of pages long, only has about 100 algorithms, okay? So even though it's huge, the actual collection of blocks of knowledge, when we take away, as you said, all the schooling necessary to get there, is not so big, which for us, unless we assume that there's some big, collection of human knowledge in reasoning that we're not exploring right now and that we should explore, it kind of points out that the basis of behaviors that we need to computationally reason inside a model, for example, is probably not that big, right? So there is a hope that you could learn something like all the algorithms inside CLRS and then use that as a general purpose tool library that helps your agent pick out a particular reasoning procedure when it needs it. Yeah. So this is kind of the general hope, I would say. And specifically, there are these collections. I mean, even in CLRS, we have 30 algorithms. That's not as big as 100, but it's already covering a lot of the standard behaviors like sorting, searching, pathfinding, geometry, string matching, right? All of those are skills that every software engineer likely needs to carry around in their toolbox in their day-to-day lives. And most of what they do is usually some kind of combination of those kind of units of reasoning, right? So now the question is, if we have a system that is generally capable of thinking about these kinds of units, and then sometime in the longer future, properly composing these units and selecting them at will, then at that point, we have a general purpose reasoning agent, right? This is maybe how it would tie into a kind of a longer term vision, if that makes sense. But that's the dream, more or less.
Yeah, that makes sense how that fits into the longer term of DeepMind. And maybe summarizing, you would not hire a computer scientist who has not read the CLRS book, and you would not trust an AI who doesn't know some of the algorithms pretty well, at least.
I mean, yeah, I mean, when I say I wouldn't trust it, I basically, like, if it doesn't internalize what it means for all of these things, that all of these things are doing, unless you can scrape these descriptions easily from the internet, I would not expect that behavior to magically emerge, like in all instances, just by doing a trick, like asking the model to, think a couple of steps or something like that.
And one more thought that I had, like there's been, this pretty major release of OpenAI Codex, right? OpenAI Codex writes codes and algorithms, but it has never actually seen input-output pairs or like being able to reason about generalization or anything like that. Still, it seems like a pretty viable approach. How do you contrast those two sort of lines of research?
Yeah, so first of all, maybe it's a good point to mention that just like OpenAI's Codex at DeepMind, we have developed something that's in a very similar vein, which is AlphaCode, right? So DeepMind has definitely been thinking in this direction also. And the way in which I would delimit the two, well, something that we like to call program induction versus program synthesis. So essentially in program induction, which is what the Algorithmic Reasoning Benchmark is itself a member of, you are learning a program and you're sticking it inside the weights of a neural network, okay? Whereas in program synthesis, you're learning to produce a program. So you're actually producing something that can be executed on some kind of virtual machine, right? There are many benefits to producing code. You can verify its correctness. You can, talk about its various properties in terms of time or space complexity, all of those things that with weights of a neural network, you cannot always say very clearly. So there are many, I think, clear-cut benefits to also explainability, of course. Like pseudocode is much more interpretable than matrices of weights, right? So that's the main difference, and I think it's super promising. One of the things that currently, I'm not ruling out that in the future neural algorithmic reasoning could be very much oriented towards learning synthesizers, like the ones that you see in AlphaCode or Codex. However, a synthesis operation is fundamentally a discrete operation. You need to produce discrete blocks of code, and you have to, like for the step-by-step, then you need to validate that some intermediate code makes sense, and then you need to repair it in a certain way to do the next step, and so on. Basically, whereas in our approach, you have weights, and those weights are differentiable with respect to everything your model is doing. So I will just say our current approach of induction plays more nicely with the gradient descent style of learning with which we train neural networks nowadays. So I just think that in this particular class of pipelining, neural algorithmic reasoning is going to be better embodied using program induction than program synthesis. That being said, it's only a very simple and right now kind of answer to a question that's more deeper and general. And I've talked to many program synthesis experts over the years, and we believe that in the future there will be some kind of glorious convergence where a synthesizer like AlphaCode might be able to make advantage of some of the things that we learn, and we might be able to make advantage of some of the things that synthesizers are able to do well. So I would say, regardless of which direction you care about more, I would say certainly certainly watch this space because there's going to be really exciting things coming in the future.
And just one kind of a wild off question. When we get quantum computers in the maybe near or further future, how will that change sort of this algorithmic reasoning?
It's an interesting question. I would say that, so I actually made a remark about quantum computers as a model at the beginning of our conversation, where I said that like algorithms as a language will probably stay relevant and important regardless of what the model of computation is. So even on a quantum computer, you might be able to learn quantum algorithms, for example. That's what it would be best suited for, I guess. And I already know from my interactions and collaborations with some quantum engineers that basically there's a lot of interesting algorithmic stuff to do there. One thing I would remark with quantum computation now is that it's very fundamentally memory limited, right? So the number of qubits you get access to currently is very low. Yeah. And as a result, people in quantum machine learning generally seem to be trying a lot to exploit anything they can exploit about the problem they're solving to reduce the requirements of the parameterization. And as a result, the ideas from, say, geometric deep learning, where you are effectively controlling your model function to respect certain equivariance properties, essentially that reduces your parameters. And that's why quantum machine learning people love geometric deep learning. There's been like 3 or 4 separate quantum geometric deep learning papers that came out within a week of each other or something like that. So in a very similar vein, I would be very unsurprised if quantum algorithmic reasoning becomes relevant going forward in a similar vein, because doing it right might mean we save a lot on time of training, a lot of memory requirements, and these kinds of things.
Thanks. And then one last question that I have to ask, kind of as being from Zeta Alpha. So obviously the progress in this area is going very fast, and research literature is exploding, thousands of papers at each major conference. So how do you kind of, for yourself and within DeepMind, how do you kind of manage to read so much? How do you keep track of the literature? What kind of approach do you use to know what's new, hot, and relevant?
It's a very, very important question, I think, going forward. And sometimes getting to connections earlier can save one a lot of time if they're aware that somebody did something related. So what I try to generally do, it's a heuristic that works for me, not necessarily will work for everyone, but I tend to have these kinds of, say, GitHub repositories that generally track interesting papers of a certain type. And whenever there's a big conference, these repositories get updated, and I can usually then query for certain terms or keywords that I care about and see if there are any papers I should look at. I also search by authors because I know who are most of the authors that do significant amounts of work in the space. As I said, Steffi Egelka's group at MIT is a great example. So if I search for these kinds of people, I can usually find the progress that's happening quite quickly. At least so far, it was a good heuristic. It might not stay a good heuristic as the field picks up more traction, but so far it's been good. And lately, one thing I found very interesting is you can also, to some extent, use machine learning over these kinds of texts by encoding them or their abstracts or whatever. And you can use that to give suggestions for what are likely the most relevant papers on a particular conference for the particular, previous research output that you've had, for example, right? And I've been trying to make advantage of these kinds of systems when it was possible to also get some recommendations. Like I used to do this before I would physically go to a conference. You get like top 10 recommendations on which papers are likely to be most relevant to you. And usually those recommendations tend to be quite accurate because it's not that much of a hard problem usually to figure out which keywords line up the best with what you've done before. I don't think it requires a very deep level of understanding usually. Yeah. Anyway,
right.
Those would be the main kind of directions I would use.
Thanks. So it's a little bit of a setup, almost as if we had agreed that that's actually one of the problems we're working on. So these kind of neural network-based fingerprints of research papers and how to use them for search and recommendations. So for all of you in the audience who kind of recognize this problem of staying up to date on the latest research in AI, follow our interviews, our blogs and videos on YouTube, and check out Zeta.com for tracking research papers. Petar, thank you very much for the interview. It's been a really insightful conversation, and I'm looking forward to seeing more of that great work and CLRS being adopted as a maybe not a leaderboard, but a defining resource for shaping a program of research. Thank you.
Thanks so much for having me.